Today you will be learning lesson 7.3 on similar figures. Okay, your goals for today is to be able to identify transformations needed to create similar figures. You'll be creating similar figures using those transformations, and you'll calculate the scale factor used to create similar figures. So some vocab to start us off. Okay? Similar figures are figures that are the same shape, but now they are not the same size. Remember, if they're the same shape and the same size, then they are called congruent figures. Okay? So if two figures are similar, one can be obtained from the other by a sequence of transformations and dilations. Dilations have to be included this time. So it could involve a rotation, reflection, or a translation, but now a dilation has to be part of it. Okay? And the symbol for a similar figure is just that little squiggly line that was on top of the equal sign in that congruent symbol, but just that little squiggle by itself is referring to similar figures. Okay? When you have similar figures, the corresponding angles are still congruent, which means they're exactly the same. Okay? But now the ratios of corresponding side lengths are equal. The sides themselves are not equal, but the ratios of those corresponding lengths are. So to determine if two figures are similar, what we do is we make sure the figures are the same shape. If you're comparing a square to a rectangle, they are not similar. Okay? They have to be the same shape. Okay? Then we write the ratios of all sets of your corresponding side lengths. Okay? The way I like to do it to make sure I always have them the right way, because you have to have them in that same comparison, is always put the small figure over the big figure. Okay? That way I make sure it's always that same ratio, small over big, small over big, small over big. And then we simplify those ratios. And if they all simplify to the same number, the figures are similar. If they do not simplify to the same number, then they are not similar. So, the way we do this then, okay, because not all shapes have perfectly nice sides that we can count, and not all of your problems are going to give you the exact side length. Okay, so if they give you a diagonal length for a side, but they don't tell you how long it is, what you need to do is make a right triangle and use the Pythagorean theorem to find the side length. Okay, so right here in this shape, okay, this is a quadrilateral, but it doesn't have straight sides. We have a sideways side right here for C. Okay, so what we're going to do is we're going to use that side, and we're going to make a right triangle. Because I'm going to be able to figure out what A is, they're going to give me what B is, and then I can find that diagonal length of C by using A squared plus B squared equals C squared. Okay, if the square root is not a nice number, so it doesn't simplify to that whole number, it's not a perfect square, what we do is we leave it in radical form. Okay, we leave it as a square root. We leave it as the square root of 18, and we do not round that to the number. Okay, when we solved square roots before, we always rounded to the nearest tenth or to the nearest whole number. We're not doing that for this lesson. We're leaving it as that radical. So let's look at an example. Okay? Determine if the two triangles are similar by using transformations. Okay? So we know two of our side lengths. Okay? They're these two over here, S and T. Okay? I know ST is 3. Okay? So I'm going to compare my short sides. Remember, we need a ratio, and we're going to use small over big, just because it's easiest if we always set them up the same way. Okay? So on my small figure, the shortest side from S to T is 3. The shortest side on that big triangle from P to Q is 1, 2, 3, 4, 5, 6. Okay? So there's a ratio of my side lengths, and if I simplify that, it simplifies to 1/2. Okay? So then I need to check my other known side. Okay, so let's go with that long leg, because they're right triangles, they're called legs, so we can call it the long leg. Okay, So on my small triangle, this one right here, right, we're going to go from S to T. Oops, sorry, from U to T. So if I count how long it is from U to T, we have 1, 2, 3, 4, 5 on the small figure. And that long leg on our big figure is from Q to R, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I simplify that, I again get 1/2. Okay, so the only side length we have left now is our hypotenuse. Okay, the problem with that is they don't tell me how long it is. So what I need to use is that Pythagorean theorem. Okay, so remember this is C, we have A, and we have B. So using my side lengths, I have 3 squared plus 5 squared equals my C squared. 3 squared is 9. 5 squared is 25. And 9 plus 25 is 34. Okay, so 34 equals C squared. So to solve that, I need to take the square root of 34. Okay, but that is not a very nice number. Okay, so what I'm going to do, like I said, is leave it as that radical. So I'm just going to say the hypotenuse of my small figure is the square root of 34. Okay, so now I need to do that same thing on my big figure. So we said that P to Q was 6, so I have 6 squared. And we said that Q to R is 10. So I have 6 squared plus 10 squared is going to equal that side. That's C squared on that triangle. Okay, so 6 squared is 36. 10 squared is 100. 36 plus 100 is 136. And that equals C squared. Okay, so to solve that equation, I take my square root. And I know that 136 is not a perfect square. So I'm again going to leave that as the square root of 136. Okay, because these aren't my final answers, I don't need to actually evaluate them. Okay, but all I need to do now is type that into my calculator. Okay, so if you type in the square root of 34, okay, then hit divided by the square root of 136, what you get is 1/2 or 0.5 on your calculator. Same thing. Okay, so now when I compare all these answers, I have one side length with a ratio of 1/2. The long legs have a ratio of 1/2, and the hypotenuses have a ratio of 1/2. Since all those ratios are the same, that tells me my figures are similar. Okay, and the reason that is, okay, is because all those side lengths have the equivalent ratio. Okay, so let's talk about this in forms of transformations. If I'm similar, remember it's still going to be using transformations, but it has to be a dilation. So if I look at triangle STU, okay, what they actually did to it was they reflected it over the y-axis, okay, and then they dilated it. Okay, and for this one, we're not worried about how much bigger they made it. Just that you recognize that that dilation is in there. Let's try another one. And this one should be a little bit easier because if you notice, there is no diagonal side lengths. Right? So, starting first, when we have rectangles, we should know that the short sides are the same as the long sides. So for this one, we really need to just check our short sides and our long sides, because both the short ones are the same and both the long ones are the same. And remember, when I write these ratios, just to keep it consistent, I'm using my small figure over the big figure. Okay, this is just how I'm setting up those proportions, those ratios. Okay, so on my small figure, okay, this is the small one, so that's one we're always going to start with. Okay, this is the big one. Okay. Wrong arrow right there. Big one down here. Okay? So, on my short one, or my small one, the short side is 1, 2, 3. Okay. On the big one, that short side is 1, 2, 3, 4. So the ratio is 3 to 4, and that one doesn't simplify, so I just need to leave it like that. Okay. So now when I check the long side, so from T to W is 1, 2, 3, 4, 5 on my small figure, and the long side, so like X to Y, is 1, 2, 3, 4, 5, 6, 7. Okay. And that one doesn't simplify. So now I'm comparing a ratio of 3/4 to 5/7. Okay. And since those are not equal, that tells me that these two rectangles, even though they're both rectangles, are not similar. Okay. That's because their corresponding side lengths do not have equivalent ratios. And when that happens, our figures are not similar. So we'll try one more of those with a diagonal side length. Okay, so when you have these one with diagonal side lengths, my first suggestion to you is to always check the ones that you can count first. Because in order to be similar, all corresponding side lengths have to be that equivalent ratio. So if you check the short sides and they're equivalent to the long sides, okay, then you have to check the next one. But if those first two are already different, then you don't need to check anymore. So let's look at these figures. Okay, and again, we're going to use that same proportion or the same ratio of the small figure over the big figure. Okay, so this top one is my small one, and the bottom one is the big one. Okay. So in order to find out if they're similar, I'm going to start with those short sides. Okay. Or in this figure, we could actually call those the tops of those shapes, since there's 4 sides. Okay. So if I look at my small figure from E to F is 2, and on my big figure, A to B is 3. That ratio doesn't simplify, so I leave it as 2/3. And then let's go to the bottoms. Okay, we did the tops, let's check the bottoms. Okay, so on our small figure, from H to G is 1, 2, 3, 4. And on the other one, our big one is what from D to C is 1, 2, 3, 4, 5. And that ratio doesn't simplify. So I'm comparing 2/3 to 4/5. Okay? Those are not equal, so what that means is these two shapes are not similar. Again, if you had to explain it, you would say because the ratio of corresponding side lengths are not congruent. So on this shape, okay, since those two already didn't match, we don't need to check the left and right ratio because the top and bottom were already not equal.